Hi everybody, welcome to this webinar looking at how AI can support asset management and predictive maintenance. We're delighted that so many people are interested in this topic and thank you for taking the time out of your day to attend. My name is Robert Driver. I'm the Marketing Manager for IFM Engage, which is the knowledge transfer arm of the Institute for Manufacturing, and I'm the host for today's webinar. So before we get started, I'm just going to do a bit of housekeeping. Ajith, if you could just move on the slide. We're recording the session and we'll send out a recording to everyone that's registered for access after the session. Please can you use the Q&A functionality to post questions to Ajith that you want to answer during the Q&A session. And please use the chat functionality if you have any technical questions and we will do our best to help. Moving on to a little bit about the IFM. So the IFM, the Institute for Manufacturing, is part of the University of Cambridge's Department of Engineering. Our activities focus across three broad areas. Firstly, research. We conduct research across a wide range of manufacturing-related topics, combining expertise across management, technology, and policy to address the full spectrum of manufacturing challenges and issues. Education, we provide both undergraduate and postgraduate education programs. They combine a comprehensive grounding in engineering, management, and economic principles with practical application in industry. And then finally, practice. We work with organisations to transfer and apply tools from the IFM and approaches through services including consultancy, courses, and memberships. A lot of this work is done through the knowledge transfer arm, IFM Engage. And throughout all these strands of activity, we work extensively with organisations across academia, government and industry. Moving on to today's speaker, just to introduce Ajith Parlikad. He is the Professor of Asset Management here at the IFM. He's the head of the Asset Management Research Group, so is in a perfect place to cover how AI is being used to support decision-making in this area of asset management and predictive maintenance. So I'll hand over to Ajith now to get started on the main content of the presentation. Thank you.
Thank you, Rob. Hopefully you can see me and hear me clearly. Great. Good afternoon, everyone. So this is going to be the agenda for the next half an hour or so. I'm conscious that some of you might have attended the previous webinars in this series where we were talking about machine learning and artificial intelligence, but in other contexts. But for completeness and for those who had not been able to make it to the previous webinars, I will touch upon what machine learning and AI means, and then go into the topic of the seminar, which is how we apply examples of applications of AI in maintenance and asset management. We'll have some time for questions at the end as well. So to start off, what is machine learning? A very simple definition of machine learning, as you can see there, is machine learning allows programs to computer programs to improve their performance with experience without being explicitly programmed. So that last phrase there, without being explicitly programmed, is really important. Many of the computer programs that you're familiar with, for the program to make decisions or to make choices, you write a series of if-then-else statements, right? So you program a set of rules and the computer then follows those rules. Machine learning is quite different from that in the sense that you don't actually tell the computer what exactly to do. So it learns from experience, it learns from data, and that's the key difference. The other terminology that's often talked about in this context is artificial intelligence. And if you read articles, papers on this topic, you will see that AI and ML are often used kind of in a synonymous manner. They are used in an interchangeable manner. But in academia and in our world, AI is often defined with a broader sense. So you can see the kind of not clear definitions, but explanations of what AI actually means. So AI is about, or artificial intelligence is about, creating a machine that can communicate and behave in a way that is indistinguishable from a human being. And that's the Turing test that everyone talks about. So AI is it's a broader concept than machine learning. And machine learning refers to the learning part of AI. Machine learning refers to that process of learning from historical data sets and then applying that to the current world is where AI comes in. But keep in mind that AI is not all about machine learning and learning from data. There are other types of AI as well. For instance, there's this thing called symbolic learning, where we try to represent human knowledge in the form of symbols and connections between the symbols and concepts and so on, and use that as a way to make computers drive decisions. So that's AI, but not supported by data. So hopefully that has given you some kind of context to think about when people talk about machine learning and people talk about AI, right? Okay, so let's get into what kind of problems do people use AI and machine learning for, especially in the context of manufacturing. So if you think about a manufacturing organization, what are the kind of questions that people working there need answers to in order to kind of operate successfully? So things like, which suppliers should we choose? Or from an inbound logistics point of view, where is my stuff? Is it going to arrive on time? How much do we need to order? Or if it is about selling, the products and services you're delivering, then what kind of sales channels are best? What kind of promotions are working, and what kind of promotions should we start and stop, and so on. Once we sell it on to customers, you might want to understand, are there any quality issues reported? What are the big problems that the customers are facing, so we can actually inform our design team about redesign of our products, right? So these are the kind of questions that AI and ML are trying to answer these days. And as I said before, machine learning it stands upon data. So what kind of data are we actually talking about? So if we think traditionally, the common sources of data in the manufacturing world are what you can see here. Data from your ERP and MRP systems, your process control, statistical process control data that monitors the quality of the products that you're making. In the retail environment, we all use your Tesco Club card and Sainsbury's Nectar cards and so on. Data from that, data coming back from customers about warranty claims and so on. So those are the typical data that you have. And pertinent to this talk, maintenance logs, companies that capture all the maintenance activities in a good manner, they'll have good maintenance logs as well. What you can see here, common to all of this, is that most of this data is of low volume, low velocity, and since the data is not coming so fast, the variety of data is low, and it's mostly structured. But what we have these days is with the advent of things like Internet of Things, sensors, and so on, we have the ability to collect a vast amounts of data and vast amounts of different kinds of data, things like telematics. And this is really applicable to this particular context of predictive maintenance and asset management as well. Sensors that you are able to deploy on machines, wired sensors or wireless sensors and so on. Smart products that are able to communicate while they are being used by the customers. They are able to communicate and send you back some feedback, some data, and other sources like social media and websites and so on. Probably not that relevant to predictive maintenance, but that's what companies are now using. Compared to what you saw before, what you can see here is that here we have high volumes of data and high velocity of data. If you can imagine the amount of data produced by Facebook on a typical day or even a typical hour, it'll run into terabytes, right? And it's also high variety of data. And most importantly, the kind of data that we have now is unstructured as well. And that presents a lot of challenges. Okay, so that's just to set the scene. Now, what I'm going to do is over the next 3 or 4 slides, talk you through some very basic examples of what machine learning problems are. Okay. So let's look at this first problem. It signifies the first kind of machine learning, or first type of machine learning. So you're given a series of numbers, so 1, 2, 3, 4, 3, 8, 5, 5, 7, 6, 9, 0, and so on. And I'm telling you 1, 2, 3, 4 means 1, 3, 8, 5, 5 means 3, and so on. And then at the end, I'm asking a question: what does 9045 mean? Right? So you're given some examples of the state of the real world, or state of the world, for example, and I'm then asking you, based on those examples, can you give me an answer to this new example or a new question? So what you're typically trying to do here, as I'm speaking, is trying to find a connection between the numbers on the left-hand side and the numbers on the right-hand side, right? And you're trying to figure out a logic through which you can answer the last question. So those of you who have actually cracked the puzzle, the answer is quite simple. The number on the right-hand side is the sum of the digits of the numbers on the left-hand side. And if you get a double-digit number, you again add the digits, you get the number on the right-hand side. So you can answer the question post, right? Another example. So that was quite straightforward. This example now, I have got a red square that is yes. A green circle means no. A red circle means yes. And now I'm asking a question: what does that green square that is actually not filled mean? Now, again, you'll start the whole process of figuring out what is the basic rule, or the relation between the left-hand side and the right-hand side. Some of you might have come with some conclusions. So, for example, it might mean that red means yes and green means no, so I'm going to answer no. But then some of you might be thinking, is it a square versus circle? Is it filled versus unfilled, and so on? So, and many of you might actually say, actually, we don't have enough data to answer this question. And this is a typical problem in machine learning as well. The question is, do we have enough data? Do we have enough variety of data in order to learn these rules so you can answer the question? So this type of problem is called supervised learning, where you're actually given a number of examples where you know the answers to, and you learn the logic or the rule based on these examples. Now, the first thing that we do when we are building a machine learning model is to do this thing called feature extraction. So really try to understand the features of the data, or the nature of the data. So here it might mean the color, the shape of the figures, the number of corners, the size, for example, position, orientation, and so on. All of these features with the questions and answers are fed into this machine learning model. It learns the relationship between the questions and answers based on the given data, and tries to figure out what the answer should be given a new example. Okay, so that's what we call supervised learning. And the examples of supervised learning in the real world, you'll see plenty of them out there. Facial recognition. So when you take a picture using your phone, if you've got a link to Google Photos and so on, the Google will immediately start recognizing some of the images, some of the pictures, some of the faces in your pictures, right? So this was a photo taken by myself, and Google immediately recognized my face and some of my researchers' faces as well. In manufacturing, on the right-hand side, a good example of this is anomaly detection or fault detection. So here, this example is showing a supervised learning approach to learn and then tell us whether there are any defects in the caps. So you can see that, first of all, this algorithm is detecting all the caps, that is, of the bottles coming through the conveyor belt, and one of those caps, the one circled or noted in orange, you can see a crack on the cap, and it is actually detecting that there is a crack there. And that's an example of a typical classification problem. There are other examples. So one of the common emerging ones is autonomous driving, where this is what a car actually sees. I'll mute the voice there. This is what an autonomous car sees. It can actually see all the vehicles on the road. It can see pedestrians on the side and so on. It can classify them as vehicles, pedestrians, cyclists, and so on. Use that to then figure out what the risk is on what risks are on the road, and then drive accordingly, or inform the controls to drive accordingly. Moving on, so that was the first type of learning. The second type of learning here, so here the question is, so I'm showing you 4 pictures, which one is the odd one out? So I'm not telling you what these pictures are of. I'm not telling you what you should be actually focusing on in these pictures, but if I just ask the question, which one is the odd one, even a child would be able to answer. The sock is the old one, the other ones are fruits, right? Now, a computer typically will not learn the fact automatically that they are fruits, but it will probably realize that there are these circular things with kind of green things on top, and there's this one object where it doesn't, those things are not there. So it will classify or cluster these 3 fruits as one cluster and the sock as another cluster, and this is called an unsupervised learning problem. And in other words, it's also called clustering. Another example is these keys. Now, if I ask you to group these keys, some of you might say there's a golden set of keys and there's a silver set of keys. Some of you also might say there are actually these keys that are actually very decorative, and there are these keys that are very normal, right? So one of the things with unsupervised learning is that you are actually not giving the computer what we call the ground truth is. So in a classification problem, you're giving examples with these true values or the truth, whereas in an unsupervised learning problem, that is not there. So there are more than one ways in which you can actually cluster these examples, and computers might also do the same thing. They might do clustering in different ways. And also another question is, how many clusters do you actually want the computer to make? So this is an example of unsupervised learning called clustering. The last type that I want to talk about is this thing called reinforcement learning, right? Reinforcement learning is very, very different to what we discussed until now. Here, you don't actually tell the computer what to do or how to do it. So in the previous case, we actually told the computer that I want you to cluster them into different groups, right? Here, you don't even say that. You don't tell the computer what to do. What you do is you give the program a kind of reward when it does the right thing. And in some reinforcement learning programs, you give a penalty to the program if it does the wrong thing. And all you tell the computer to do is your job is to maximize your reward, right? So that's what is called reinforcement learning. And this is here I've got a couple of examples of not computer examples, but animal examples, where one is a mouse that is able to detect landmines, pigeons that are able to look at pictures and identify breast cancer. And this is typically the way human beings and animals and birds learn, by getting rewards or penalties. When you do a good thing, you get rewarded. That kind of encourages that good behavior, right? And that's what we are trying to achieve with this as well. One of the examples that are quite interesting, what I'll do is I'll run through this very quickly. Here, there's an example where these researchers taught a computer how to play Breakout. So people who have played this game Breakout before. Actually, I'll forward this. Yes. So this game called Breakout, where you have this paddle and a ball, and the objective is to hit through those bricks, right? Now, what they did here was, it didn't tell what the game was. It didn't tell what the objective of the game was. All it knew is that when it does certain things, it gets points. When it does certain other things, it actually loses a life. And what they are trying to show here is in a few iterations after 100 games, 300 games, the computer automatically learned the rules of the game, and it also optimized the way it needs to play in a way that even human beings could not play. So if I fast forward, you'll see that, let me just turn the, what you can see there, what the computer has done is it figured out that if you make a hole through the wall of bricks, and if you can get the ball on the other side, it will actually speed up the whole process. It'll gain the most. And the funny thing is that the computer figured it out all by itself. Yeah, and that's the power of reinforcement learning. Okay, so let's move on now, and let's talk about how all of these things are applied in predictive maintenance. So before we move on to predictive maintenance, just to kind of set a context, how did we get here? So we started off in the world of maintenance by thinking, okay, maintenance is all about fixing when things fail. And for a lot of things, we still do that. And for a lot of things, it actually still makes sense. So that's what we call a first generation thing, corrective maintenance, fix when it fails. We then realized that that poses a lot of risk, and planning your maintenance activity or trying to prevent the failures by planning maintenance activities before they fail is often beneficial. So most of our companies, we have a set of assets where we have our scheduled or planned maintenance or preventive maintenance plans, and a number of assets where we just do corrective maintenance. Now, with the planned maintenance activities, a disadvantage is that once we decide that the pumps are going to be inspected every 6 months, or filters are going to be replaced every 2 years, we apply the same rule across all our pumps and filters, right? Now, some of these pumps or filters, they might be used more heavily than others. So sometimes we might be doing over maintenance. Some of the times it will be under maintenance, and you'll still see some faults. And this is where condition monitoring comes into picture. If we can somehow track the condition of the asset over time, we should be able to, theoretically, we should be able to do maintenance at the right time and at the right level. Yeah, and that's where condition monitoring and this term called condition-based maintenance comes into picture. Now, with the advent of all these machine learning approaches, what we are able to do is, if we are able to monitor the condition of an asset over time and until they fail or until they are maintained, we are able to build a set of historical data set that we can then use to train machine learning algorithms, and then let the machine learning algorithms tell us when something is wrong, tell us when something might go wrong in the future as well. And that is what we call predictive maintenance. So we are trying to predict what might go wrong in the future. So what is the bare bones of predictive maintenance? So as I said before, it all starts with monitoring. So either using sensors, whether it is wired sensors or wireless sensors, somehow monitoring the condition of this machine, using that condition monitoring data to estimate what the state of the components are, whether they are good, whether they are bad, they are degrading, and so on. And then using that evolution or understanding of the evolution of the state of the components to predict what the remaining lifetime is going to be. Once you can predict the time of remaining lifetime or the time of failure, you can then feed that into a maintenance management system to then decide, okay, what are we going to do? When are we going to act? When are we going to intervene on the asset? Okay. So just to touch upon condition monitoring. So when it comes to condition monitoring, the kinds of things that we want to collect data about are the ones that I can have shown on the right-hand side. So of course, to equipment or tool condition data. So if you can somehow measure wear, for example, or if you have rotating components like bearings in your equipment, and when they rotate, of course, they produce vibrations. So if we can monitor the vibrations that are coming off, it might give you an idea whether things are going wrong or not. Other kinds of data is data about the process itself. So what is the feed rate? What is the speed? What is the depth of cut? All of those things that you're actually programming your CNC machine, for example, all of those things are going to be useful to let us know what So for example, when you're getting data off the condition monitoring sensors, you need to know what the machine is actually doing at the time when it is producing those sensor data, right? And that comes from the process data. A lot of information can be gained by just monitoring the job or the product itself, not the machine, but the product. Because if the machine is not working properly, if the machine's condition is bad, that might be reflected on product quality. So if you monitor product quality, you can indirectly do condition monitoring on the machine as well. And the last thing I also would encourage you to think about is the environment. What is the temperature, humidity, air quality, and so on of the environment, if you think those parameters might affect the condition and the quality of your product and services. Okay. So that's the kind of data that you might want to collect. Now I get into the fun part. What can you do with the data? So what is predictive maintenance all about? What are the different things we can do? The first thing first example here is fault diagnostics. So this is an example where we are monitoring bearings using vibration sensors or accelerometers, and the graphs on the left hand side, the red set of graphs and the blue set of graphs, one set is showing by acceleration in one axis, and the other one is in the second axis, I think X and Y axis. What we are doing here is to apply a typical classification kind of an algorithm. So here it's using neural networks where the data is coming through, the raw data from the accelerometers are coming through on the left-hand side, and on the right-hand side, you can see 4 boxes. And these boxes really denote the final labels. So what we are seeing here is that bearings can fail due to different reasons. There are different failure modes for the bearing. The bearing can have cracks, it can have kind of rough surfaces inside, the bearing balls can corrode and can have pitting. So there are 3 types of failure modes, and this algorithm is trying to see how, given a set of data, can we actually say what kind of failure it is. And of course, what we're feeding here is the ground truth data, so that we'll be feeding a lot of data that shows good behavior of bearings, a lot of data from bearings that have got cracked surfaces, a lot of data from bearings that have got corrosion and pitting and so on. So this algorithm learns from this historical data, and given a new data, it will be able to tell you what the potential fault might be. This is an example where we are not just looking at one component. So the previous one, we were just looking at bearings, right? So here, the same logic is applied to an entire machine tool where, again, we are using vibration data in this as well. But what it can do in terms of fault diagnostics is it can tell you whether the bearing is damaged, or the gearbox is damaged, or there is a problem with misalignment in the output shaft. So there are 3 types of faults occurring from 3 different parts of the machine tool, but this can be diagnosed using a common vibration data set. What you will see when you see examples of machine learning is this figure that you can see on the right-hand side of those boxes. It's called confusion matrices, and it's typically used to determine how accurate your machine learning algorithm is. So this confusion matrix, what you can see on the x-axis, if you will, or the columns actually denote the actual condition, and the rows denote the predicted condition, or what the machine learning algorithm is saying what it is. And in this case, what you can see is the accuracy is quite high. You can see zeros in the purple boxes and big numbers in the green boxes, which means that it is not giving you many true positives or false positives or false negatives. So that's a good way to represent the accuracy of a classification algorithm. Another thing that you can do with the data is anomaly detection. So, and this is typically what many so-called predictive maintenance solutions offer. I'll talk about the challenges later, but because we might not have enough data to train an algorithm, what we might be able to do is to train an algorithm using an unsupervised learning approach to say, okay, just learn what is normal, and if you see that is anything that is abnormal, tell me that it is abnormal. So it's more like a clustering approach. So you create a cluster, 1 or 2 clusters, and then based on those learned clusters, what you're trying to get the algorithm to say is, given a new data set, does it belong to those known clusters or not? So this is an example where we applied to Felixstowe ports, the cranes on Felixstowe ports, where we did not have that much historical data sets or historical knowledge to base our algorithms on. So we started collecting data from, we deployed sensors on the big motors on these cranes. We collected the data from them. We also collected data from the PLC that allowed us to understand what the crane is actually doing at that time. What we did was we created these clusters of data types or data sets that represented different kinds of operations that the crane is undergoing. So if the crane is lifting a container or dropping a container, moving without picking up a container and so on, we learned those patterns of vibrations and temperature and so on that the crane gives. And then given a new data set, the algorithm is able to say, okay, I haven't actually seen this kind of data anywhere so far, so it might be an anomaly. Where you're not sure whether it is an anomaly, so in this particular case, what we said was, okay, let the algorithm tell us that there are these discords, we call them, and if there is a discord, we can ask the engineers to go and check whether there is a problem or not. Now, if there are lots of discords, one of the things we can actually do is to say, okay, on an hourly basis, we set a threshold. If we see more than that number of discords from the data, it might be a sign that something really is going wrong. So go and check the crane. The last example is failure prediction. Of course, this is the kind of holy grail where we want to get to. Can we actually predict failures into the future? Again, an example from bearings, where using vibration sensing, what these researchers are trying to do is to predict the remaining useful life of these bearings. On the right-hand side, you can see 2 graphs where the blue line is the actual time to failure. So you can see a straight line there. And the red line is what the algorithm is actually predicting as the remaining useful life. You can see that the algorithm is not completely accurate, but it is more or less, it's following the trend. At least you know that it is approaching a failure time. To extend this thought, what we have done with Scania and other companies as well is to look at a fleet of equipment. Now, one of the problems, as I said before, is that we don't often have enough failure data. And the other problem is that assets are very homogeneous. So if you take trucks, for example, one truck goes through a completely different environment and life than another truck. They might be used in a different way. They might be used in a different kind of setting for a different purpose. So a model trained for one truck might not be nicely applicable to a model for another truck. So what we try to do here is, based on the data, we first do a kind of unsupervised clustering kind of thing, where we say, okay, from all the data, we can group trucks in different ways based on their behavior, and then train different algorithms for each of the cluster of the trucks. So given a new truck, what our algorithm does is to first of all try to figure out what kind of truck it is. And then as it gets more and more data, it switches between these clusters if necessary and predicts the remaining useful life. And the graph at the bottom there on the right side picture, that is the prediction of the remaining useful life as time goes on. And as you can see there, when in the early part of the life, the uncertainty is very, very large. We don't really know what the remaining useful life is. As we get more and more data, the kind of uncertainty band gets tighter and tighter. Yeah. I'll skip this. The last thing I want to actually show an example of is how do we actually bring all of these things together. So it's a good thing if we can detect and predict failures and so on, but we need to be able to drive decisions using that, right? On the left-hand side, what you can see is an example of a piece of work we did with Rolls-Royce, where we were trying to understand the remaining useful life, not just in terms of time, but in terms of 2 parameters. So the number of landing and takeoff cycles, as well as the flying hours. So the engine's life depended on these 2 factors. Now we are able to build a model that tells us, according to these two parameters, what the remaining useful life is. So one of the things that airlines might be able to do here is if the algorithm says that the remaining useful life in terms of the number of landing and takeoff cycles is very low, but the other one, for flying hours, you've got a lot of life, what they can do is to try and fly the engine on longer routes. So you're getting more life out of this engine. That's a useful thing. And on the right-hand side, what we try to do is, when we actually then plan your maintenance activities, try to use all these failure predictions and the remaining useful life information from these machine learning algorithms to say, if you're anyway taking the engine off the wing to do some maintenance, what other components should you actually replace at that time to kind of optimize your maintenance activity? Okay. Right. So hopefully that has given you a kind of a flavor of what predictive maintenance is and the different kinds of problems we can actually address using predictive maintenance. So if just a couple of slides to kind of wrap things up. First question I'm asking myself, is it actually worth it? So there are a number of benefits, as you might have guessed. We should be able to eliminate or reduce unexpected breakdowns because we are continuously monitoring our assets. Increasing the time between repairs or maintenance activities. If you are more sure about the life of your equipment, you can reduce your spare part stock, right? So spare part stock is almost like your insurance. In case something goes wrong, you need to have your spare parts so you can quickly replace them. So if you have more certainty about that, you can reduce your spare part stock. And of course, this can have an influence on insurance premiums as well, because you are running a lower risk operation. And finally, it generally increases your understanding or improves your understanding about how your machines are actually operating and behaving. Of course, this is not without costs. There's a lot of added costs when we are doing this. You need to design the monitoring system. You need to purchase and deploy these sensors and analysis tools, computers. You need to have staff who really understand data, who are able to build these machine learning models and so on. And there are these added labor costs involved in doing this as well. And finally, you're adding something to your system, which means that thing that you're adding to will require maintenance as well. So your sensors, especially wireless sensors, you'll need to replace batteries every once in a while. And these sensors can themselves fail. So you need to maintain these sensors as well. So that's the balance that I see between costs and benefits in predictive maintenance. Number of challenges, I've touched upon this. Data availability is a big challenge, and there are a number of kind of strategies we are applying to address data availability. Labeled data. So when I talked about classification algorithms, you need to have a corpus of this ground truth data. And that's what often is missing when we work with our industry partners and so on. This labeled data set is often missing. So we then fall back onto unsupervised learning with added bits of expert knowledge. Data quality is still needed to be improved. And it's just there's a lot we can do about that. And one of the things that we thankfully we as machine learning engineers, we are worried about is that failures are very rare, so we don't get enough failure data to train our algorithms. Yeah. I'll actually stop there, Rob, and put this slide in front of you, because many people ask me the question, how do we actually get started in this whole journey? And it's quite self-explanatory, so I'll leave the slide there and open the door for questions.
Excellent stuff. Okay, so thank you very much for that, Ajith. That was really interesting. We're just moving on now to the Q&A section. So if you've got any questions based on what you've seen or in general in relation to asset management or predictive maintenance, please put them in the Q&A session. So just to start off, Ajith, I had a quick question around, are there any ethical or kind of regulatory considerations that organizations need to consider when looking at AI for asset management and predictive maintenance?
Good question. Thanks, Rob. This question about ethics is very much well, you can see in the news as well. Ethics in AI. In our context, because we are dealing with data from machines and so on, I would say ethics is ethics is always an issue, but in this context, ethics is less of an issue because we are dealing with machine data. But in certain other contexts, so for example, I'm also working with the local hospital on similar areas where we are actually looking at machine data, but also to understand the process, understand what's happening, we might need to look at patient data as well. So ethics need to be really carefully thought through when we are embarking on any journey with machine learning and artificial intelligence. More than ethics, what I would be really concerned here is about security and privacy, because we are dealing with sometimes industrially sensitive data. So when all the devices that we deploy, whether they are wireless sensors or the way we store the data, whether they are stored on the cloud and so on, security of the data needs to be carefully thought through.
Okay, excellent. I've got a question here from Maxwell. Is it recommended to deploy these analysis methods in a specific kind of hierarchical order, for example, starting with supervised and then unsupervised, or anomaly detection and then predictive maintenance or predictive analysis? Is there kind of a set way that you should be looking at this?
Yeah, so there are two ways to look at it. One way is to say, in many cases, you might not have what we call the labeled data sets. So the ground truth is often not available, which means that you are often forced to go down the unsupervised learning path. But the correct answer to this question is what you need to first do is to identify what the problem statement is. So are we trying to detect anomalies? Are we trying to diagnose faults? Are we trying to predict failures? These problem statements determine what kind of machine learning algorithm we'll need to use.
Okay, excellent, thank you. Next question from Sky. A lot of the references and research are from five or so years ago. What do you see as the timeline for this to be widely adopted in industry, and what could accelerate this?
Yes, predictive maintenance is not a new thing, and especially in the research world, it's been going on for years now. Especially condition monitoring has been happening for a large number of years. I've started seeing examples of real industrial deployment, especially in large companies, quite a lot. There are a few more kind of big challenges that we need to overcome before it becomes widely adopted. One is the need for common data standards. Data standards that companies or OEMs across the board, machine tool manufacturers and other systems integrators across the board can adhere to, so we can actually get this data in a standardized format where they are interchangeable. So that's a big kind of obstacle that I see. The other thing is cost. Most of these technologies, they are affordable to big companies, yes, but for SMEs, they might see that these technologies are a bit of a struggle to achieve because of the cost involved. And there's actually one of our research programs within the IFM is actually looking at how do we actually develop and deploy these digital solutions, including condition monitoring and maintenance and so on, these kind of digital solutions in a low cost manner. So I would say biggest obstacles are standards and to cost.
Excellent, thank you. A question here from Aldo. How long does it take to create and train a model?
So the biggest time involved, or the longest time involved in this whole exercise is the bit that comes before training, creating and training the model. It's identifying the right kind of sensors, the time taken to collect enough data, and then to pre-process and clean the data is what I would say 90% of the time taken. There are for all the different algorithms that I've mentioned, there are lots of libraries out there. So developing a model itself is not going to take a lot of time. I would say, based on the frequency of failures that you're experiencing. So for example, if you are working in an environment where there are frequent failures, now say collecting data for, say, a year would be more than sufficient. But if you are operating with highly reliable equipment, then you might need to collect more data, collect more data for a longer duration of time, so that you have enough failure data to train a model. If you want to do anomaly detection, you don't need to wait that long. Perhaps 3 months, 6 months, you would start getting some early results.
Excellent, thank you. Moving on just to an anonymous question, is there a change management aspect in this kind of area? For instance, how do you bring machine learning teams and conventional maintenance SMEs to work together? They're interested in your perspectives in this kind of regard.
Yes, it's not something that I would be able to discuss authoritatively about, but definitely there's a change management piece, because it changes the way companies operate, right? If you're used to having well, especially if you have a corrective maintenance kind of a strategy in place where you wait for things to fail before you fix it, moving to a predictive maintenance kind of an approach is culturally very different. The other big cultural factors and change management factors is also trustworthiness of these machine learning algorithms. So that is also another obstacle to overcome as well. How do you convince managers to start trusting these algorithms, that they are actually providing you with the right kind of insights?
Okay, thank you. Got a question from Lena. Is this are these approaches for companies to use based on their own data only, or is there a kind of like external databases that they can tap into that can support them with some of these models?
Are there external other publicly available databases? Yes. So there are a number of databases out there, and if you do a simple Google search, you will find that there are lots of databases where you can see manufacturing data sets that allows you to kind of practice different kinds of predictive maintenance problems. You would be able to get a kind of head start using those publicly available databases or data sets, but I haven't seen so this idea of you training a model using one data set and then using that model on a completely different application and a completely different data set is, in our world, what we call transfer learning. So transferring or transferability of this model. And this is an area that is very much in research, early research, I would say. There are some successes where people have been able to develop models that can actually do some level of transfer of applications, but it's still very much in the early stages. So I would say use the publicly available data sets as a kind of a training mechanism, a personal training mechanism for you to really understand what these algorithms can do, develop some algorithms and see whether it works. But then you have to apply it onto your own data sets.
Excellent. A question from Jean-Marc. Do you think that manufacturers should firstly prioritize do you think that the first priority to machine manufacturers, especially SMEs, is to manage condition-based maintenance before they consider predictive maintenance? That way they would benefit from data collecting and also identifying the main issues that occur between two maintenances, those which should then be detected by AI.
I absolutely agree. I would actually say that it might be a three-step process, starting with just condition monitoring, with people looking at the data and trying to figure out what it actually means, then using those or setting those thresholds and doing condition-based maintenance. So now I really understand by looking at the data how the machine is performing. Now I can start doing condition-based maintenance, and then later on go on to predictive maintenance. So absolutely agree with that path.
Excellent. We'll just take a couple more questions and then we'll finish up for the webinar. So a question here, how do you deal with imbalanced data sets? Have you used synthetic data to tackle that problem?
Yes, so the issue of imbalanced data sets is a big problem. So just to explain, a balanced data set is where let's say you have 100 data samples. A balanced data set is where 50 of them are data that corresponds to a failed situation, and 50 of them are good behavior, right? So that's a balanced data set where you can feed that into a machine learning model, and it can easily classify any new data sets in terms of whether it's a failure or a non-failure. Because of our assets are very reliable, the amount of failure data in our data sets is very, very low, and that's what is called the imbalanced data sets. There are a number of different strategies to address this. One is what we call sampling strategies. So oversampling in one population. So you feed the same failure data again and again and again into the machine learning model with some perturbations and some noise added to it. Another strategy is to use physics-based models to augment this data set. So you describe the failure process in terms of some physics-based, some equations. You run simulations based on that and use that simulation to generate some failure data and feed that into the model. Another approach, which we are also actively involved in, is where we try and capture expert knowledge and include that expert knowledge into the generation of these new data sets. So yes, the ultimate process to address that is to generate synthetic data sets. The challenge is always, how do you effectively generate these synthetic data sets instead of just copying existing data sets?
Excellent. And the last question, thank you, from Akram. Would it be fair to recommend that the best strategy for robots is CBM? Sorry, apologies, I don't know what that acronym is in relation.
Condition-based maintenance program.
Thank you. Given they are already full of sensors and machine learning.
If you synonymously mean condition-based maintenance and predictive maintenance, then I would say there's potential in using condition-based maintenance and predictive maintenance for robots. I actually supervised or examined a PhD student who was doing his PhD in Germany, looking at predictive maintenance of robots. So definitely it's possible. The big challenge with robots and these machine tools are, for the end users, it's often hard to get this data from the robots. Yeah.
Excellent. Okay, I think that draws to a close the Q&A session. I'll just run through a couple of slides on follow-up and how to engage further moving forwards, and then we'll close off the presentation. So firstly, if you want to stay up to date with what's going on at the IFM and IFM Engage, please sign up for IFM Insights. It gives an overview of all the activity that's being carried out across the organisation. Moving on to the next slide. We have a range of ways, that's great, that people can get involved in IFM tools and approaches. We've got courses and events that teach about some of the latest tools and research coming out from the IFM. For example, Management for Strategy and Technology and Innovation, taking place in March. That's a course. Road mapping course in April. Digital supply chains course in May, and then we've got our inaugural Rethinking Innovation Conference on the 17th and 18th of April taking place, and we'll send out details of all of those in the follow-up email. Organisations can also look to join our memberships. We've got a range of memberships, for example, the Strategic Technology and Innovation Management Consortium, where researchers and organisations collaborate to progress topics of interest in those areas. And we've got a range of areas like sustainability, open innovation and supply chains that organisations can participate in. And then I think that's the end of the ways to engage. But just finally, a big thank you to Ajith for the really interesting presentation that you've given there today. I hope that everyone's enjoyed it, and thank you very much for all the questions and for taking part and participating today. So I hope you enjoy the rest of the day, and thank you.